Let's start the second talk of this morning. The speaker is Professor Grigor'yan from University of Belfast. The title is Analysis on Fractal Space and Work Dimension. Let's welcome.
Okay. Thank you very much. I'm also grateful to the organizers for giving this opportunity to speak in this audience. So, as it might be clear or not very clear from the title, I'm going to speak about basic analysis on metric spaces. Right? Analysis is understood in very restricted way, in classical way, integration and differentiation. So it's very elementary from that point of view. But of course, on metric spaces, there are not enough structure initially to introduce such notions, right? So I'll be talking about Ahlfors-regular metric spaces. I'll give this definition a bit later. On such spaces, there is no problem with integration. Integration, as it goes back to Lebesgue, amounts to measure theory, right? And measure theory on metric spaces, on certain classes of metric spaces, can be introduced by using the Hausdorff dimension and Hausdorff measure. Right. So this solves this problem. So the main point will be to discuss differential calculus. So how to introduce notion of derivative on metric spaces, including fractals. In fact, main examples in this direction will be fractal spaces. Well, I'll tell about them also. It turns out that while integration is determined by the Hausdorff dimension, this will be denoted by alpha everywhere, the differential calculus requires one more parameter that will be denoted here by beta, and that is called the work dimension. Maybe a bit strange term, but I'll explain why it called in this way. Right? In Euclidean space, one doesn't see this parameter because in all Euclidean spaces, this beta equals to 2. Right? It's invisible. But on other spaces like fractals, it will be larger than 2, it will be variable, and one will see it. Right? So this notion, work dimension, is central for this talk, right? And it was originated first in the theory of diffusion processes, when diffusion processes were constructed on fractal spaces. One noticed that the time-space scaling there, one can say time is space to some power beta, is different from Euclidean scaling, when typically time is distance squared, right? And this parameter beta describes the way how the diffusion process goes away in space. Right, and turns out that what is the relation of diffusion process to differential calculus? Diffusion process has a generator, this operator, so some local operator initially in L2, but it actually serves as an analog of Laplace operator, right? And that, as soon as we get analog of the Laplace operator, we can say that at least partially differential calculus is defined. Of course, it's restricted differential calculus. It doesn't have directional derivatives. For that, one needs additional structure like tangent spaces. But just Laplace operator acting on scalar functions and resulting scalar functions can be defined in such generality. So, but then the purpose of this talk is actually to show how, one of these purposes, to show how this notion of work dimension originated first from diffusion processes can be defined in purely analytic way, thus giving approach to differential calculus on metric spaces in appropriate way, in analytic way as it should be. Right. So, okay, let's go. Right. So, but I will still start with the diffusion processes and recall some basics about Brownian motion in Rn. Right. So I denote this diffusion process by xt. T is time, non-negative real time, and xt is position of Brownian motion at time t. Right. This is in Rn, and it's known that transition density of Brownian motion is given by the Gauss-Weierstrass function. This is also known as the heat kernel, as a fundamental solution of the heat equation. The transition density means that if one starts with point x, shown here, right, initial point x, and at time t, this position xt visits some Borel set A, then the probability of this event, probability starting at x, that xt belongs to A, is equal to integral of the heat kernel over the set A. Right, so this means transition density. Right, so then as I mentioned already, this is fundamental solution of the heat equation, where Laplace operator comes into play. Right, in this case, this is classical Laplace operator in Rn. Right, so this gives initially understanding of relation between diffusion processes and differential operator. Okay, now how it's all related to the notion of Vogt dimension. Assume for simplicity that initial point is the origin, and denote by tau r the first exit time of Brownian motion from the ball Br of radius r centered at the origin. In other words, this is formal definition. Tau r is infimum of all t's, so that mod of xt is larger than r. Well, another way, this is the first time when x, this position of Brownian motion, reaches the boundary of this ball. Right? X tau r is exactly the first time when the trajectory hits the boundary. Right? Then one can actually, this is random variable, right? But its expectation can be computed explicitly, and it turns out this constant times r squared. So this is exactly what I mentioned, the scaling between space and time. Time is expectation in this case. Average time is of order distance squared. Right? In order to cover distance r, one needs time on average r squared. And this exponent 2 that appears here and here is exactly the Vogt dimension in this case. All right. Similar thing can be done on Riemannian manifolds. Just mentioned briefly because it's not the main direction of this talk, but nevertheless one can say it. In this case, delta, let it be Laplace-Beltrami operator on Riemannian manifold M. And then there is also the heat equation written in the same way. And it's known that it always has the minimal positive fundamental solution, also denoted by PTXY, which is also called the heat kernel of this manifold. And this heat kernel solves as a transition density of a diffusion process on manifold M. This time xt varies, moves on M. Right, and one can also define the first exit time, tau omega, from any open set omega, right? The first time when xt goes outside omega, and one can ask about the mean exit time from the ball, or first exit time tau bxr from geodesic ball bxr, starting from the center of this ball. How much time one needs on average to reach the boundary of the geodesic ball. Right? So this can be different on different manifolds, but if one assumes that the heat kernel satisfies the Gaussian estimate, similar to the Euclidean one, right, where dxy now the geodesic distance, and capital C and small c denote some positive constant, and this sign that I read as comparable means that there are both upper and lower bounds, but with possibly different values of constant c. Right? Then, assuming that this estimate of the heat kernel is true, one can show that again mean exit time from the ball is of order of the radius, comparable radius squared, right? So that in this case, the work dimension is also 2. So but this of course requires this additional estimate of the heat kernel, but this one is known on large class of manifolds. It's actually necessary and sufficient for this Gaussian estimate to be true that the following two conditions are satisfied, denoted here by 1 and 2. One is volume growth condition that mu denotes here Riemannian measure of any ball of radius r should be of the order r to n, where n is the dimension of manifold here, right? And the Poincare inequality, well, it's not very essential how it looks. It has the same shape as Euclidean one. At this moment is not very important, right? For example, Poincare inequality is always satisfied if Ricci curvature is non-negative, and in this case, this Gaussian estimate follow also from the Liao estimate of the heat kernel on such manifolds. Right. Another example when these two conditions are satisfied is when M is a covering manifold of a compact with nilpotent deck transformation group, as one example is shown here, so-called jungle gym. But this is not very essential. These just examples that the work dimension equals to 2 can occur also in a larger class of spaces, not only in Euclidean space. Right? But now we will come to the main class of examples here, examples of fractals and regular metric spaces. So we start with the metric space MD. D is a metric, distance function, and assume that it's equipped also with Borel measure mu, right? So altogether we get metric measure space. Right? We say that this space is alpha-regular if for any metric ball, also denoted by Bxr, measure of this ball is of order radius to power alpha, where this alpha is positive number. Right? Actually, if this condition is satisfied, then one can show easily that alpha is the Hausdorff dimension of M, and measure mu is comparable with Hausdorff measure. Right? So basically, after knowing that, one can start it in different way. Assume that M is metric space without any measure, and assume let alpha to be its Hausdorff dimension, denote by mu the Hausdorff measure, and assume that this measure mu satisfies this condition too, right? Regularity. One can say then, in this case, one can speak about alpha-regular metric spaces without a priori knowing measure, right? So usually alpha-regular spaces with fractional values of alpha are called fractal. This is not really strong definition in mathematical sense, just typical usage of word fractal, right? So now I give a couple of examples of fractals. Perhaps everybody knows this, but nevertheless, I should mention that perhaps the first known examples is mathematics is the Cantor set, which appeared as interesting example or curious example to various theorems. But for our purpose, this set is not very good because it's disconnected. For what I want to discuss now, one needs connected sets, right? Although about disconnected sets, I will tell something later on as well. So another connected fractal set is Sierpinski gasket, as it's shown on this picture. So what is this? By green area is something that is the complement of this set. And black dots that you see somewhere, this is the set itself. Right? So it's constructed as follows. Here are by iterative procedure, and one starts with this triangle on the plane, right? And then removes this middle triangle that is shown by green, and remaining three gray triangles, one repeats the same procedure by removing middle green triangle, and so on and so on. In the end, one gets a connected compact set as more or less shown here. There are also many other interesting examples. I here mention also Sierpinski carpet. Here the Hausdorff dimension alpha of this set is some irrational number, right? Log 2 over log 3 over log 2. Sierpinski carpet is obtained in similar way by taking first unit square, removing the middle of the nine squares, and then doing the same procedure with remaining squares. So one gets in the end such a fractal with this Hausdorff dimension, log 8 over log 3. And one more interesting example, Vichek snowflake or Vichek tree, where it's similarly obtained from the unit square by first removing 4 green squares as here, and then repeating this procedure with remaining 5 squares. Right, and so on and so on. There are many interesting fractals discussed in the literature. And what is interesting about these sets, right? I'm going actually to show how one can define on such fractals differential calculus. Integral calculus is clear. All these sets are Ahlfors-regular. One can prove this. Therefore, integration, there is no problem. There is Hausdorff measure and so on. There is no problem with that, right? But now, to introduce differential calculus, one needs a theory of Dirichlet forms. So let me briefly discuss this theory, which was actually developed by introduced by Berlin-Denis and developed by Fukushima. Right. So we start with some measure space M with measure mu, right? And the Dirichlet form in this space is a pair EF, where F is domain, it's then subspace of L2, and E itself is symmetric bilinear form on F. We should satisfy the following properties. First of all, positive definite. It's all properties about quadratic part. Quadratic part is non-negative. Closed in the sense that F, the domain is complete with respect to the following square norm, this L2 norm plus the energy. This E stands for energy. Of course, it's an analog of energy. Right? And it's Markovian in the following sense that if F is in the domain of this form, then when we cut it from above by constant and from below by 0, the remaining, this function, truncated function, also in the domain, and energy reduces. And what is known that any Dirichlet form, of course, as any closed form, has a generator. And generator is a positive definite self-adjoint operator L in L2. This is actually the main point here. This analogous of the Laplace operator, which satisfies this analogous of the green formula. Right. So, for example, the classical Dirichlet integral in Rn, this energy of F is integral of grad F squared, is quadratic part of a bilinear form that is a Dirichlet form with domain which is the first Sobolev space in Rn. Right? And its generator is exactly minus Laplace operator, and domain of the generator is second Sobolev space. So this main example for us is to understand the role of this theory. So another example is when we start with another quadratic form involving difference operator instead of differential operator. This is double integral of fx minus fy squared divided by mod x minus y to the power n is dimension, plus some s, where s is the index of this form, which is between 0 and 2, strictly between 0 and 2, and double integrate in x and y. Then it's also, turns out also Dirichlet form with a domain which is some Besov space. I'll actually give definition of this space below. And the generator is the power of Laplace operator, power which is s over 2, that is smaller than 1, right? Understood in the sense of spectral theory. So the generator of any Dirichlet form determines the heat semigroup, also in the sense of spectral theory. This family of operator e to the minus TL. T is non-negative time again. And if this operator for any positive t is an integral operator, that is, it has an integral kernel, then this integral kernel is denoted by ptxy, and it's called the hit kernel of this Dirichlet form, or of this operator L. This is analogous of the hit kernel in Euclidean space. Then one needs to distinguish the notion of local and non-local form. These two forms that are shown here have one difference. The first one is local, the second one is not. And the definition is as follows. Dirichlet form is called strongly local if E of fg is 0 whenever function f is constant in the neighborhood of support of g, like it's shown on this picture. F is constant on the support of g, then this called this Dirichlet form is called local, right? So as a matter of fact, maybe I didn't write the full energy form, full Dirichlet form, but as bilinear form at integral grad f g, right? Or in Euclidean space, this classical one. And if f is constant on support of g, of course, this will be 0. Right? So this form, this one, is local. Right? Whereas the second one is not local. And just to complete with these two examples, the first one, of course, has the hit kernel, which is the same as I showed above, Gauss-Weierstrass function, because it's generated as Laplace operator. For the second form, which is not local, with the generator, which is power of Laplace operator, the it also has a hit kernel, but the explicit formula is not available in general, but it admits the following estimate from above and below by some constant. Right? So it has similar shape, some on diagonal decay in time, time to the power n over s, but off diagonal decay with respect to distance is not exponential like in Gaussian case, but as power function. Right. In one specific case, when s equals to 1, that is for square root of Laplacian, there is explicit formula which coincides with the Cauchy distribution. But it's again not very essential, just to give you some flavor of what can happen. Now one more notion from theory of Dirichlet form, which is needed here, is notion of regularity. Roughly speaking, it means that the domain of Dirichlet form has enough continuous functions. So formally, Dirichlet form is called regular if domain intersected with C naught of M. C naught means compactly supported continuous function. Is dense both in F and C naught M. Right? So it's enough continuous function in support. Both Dirichlet forms mentioned above are regular Dirichlet forms. Right? So why regularity is important? Because any regular Dirichlet form, this is theory of Fukushima, determines a Markov process on the space M with transition semigroup, which is exactly the hit semigroup, right? Which means that actually this semigroup applied to some function f gives you expectation of f of xt. In particular, this implies that if the hit kernel exists, then it also serves the transition as transition density of this process. This process is called also Hunt process of the corresponding Dirichlet form. Right. So this gives a relation between all these notions. Dirichlet form generator as a generalization of Laplace operator and certain Markov process. Right. So if this form is local, then the corresponding Markov process is diffusion process with continuous trajectories. And otherwise, this process may contain jump. Right. As I already mentioned, in the Dirichlet form, classical Dirichlet form with generator of Laplace operator determines Brownian motion with continuous trajectories, of course, while the non-local Dirichlet form with generator that is power of Laplace operator, it determines jump process, which is known in probability theory as symmetric stable Levy process of the index S. right? And as I already mentioned, its transition density satisfies this estimate. All right. So now we come closer to the point of this direction, right? So what we need from this theory? We need to be able to construct on some metric space strongly local regular Dirichlet form. If we can construct such one, then its generator is local operator, which is naturally can be called as Laplace operator on this space, right? So this is actually the way to construct such an operator. Although this operator wouldn't have explicit form, we wouldn't know how to compute it. In general, there are no coordinates in such spaces, but nevertheless, this operator would exist as self-adjoint local operator in L2. Right. So in this sense, we get, in some weak sense, differential calculus. Sorry? No, not necessarily, because the Dirichlet form can be constructed in different ways, yeah. But if on these spaces with symmetries, one can ask that this differential form, this Dirichlet form satisfy the same symmetries, right? In this case, on many fractals, it will be unique, right? If one imposes an additional No. That's the point. The dimension will be the same. Yeah. That I'll come to that. Right? Yeah, that's a very good question. In fact, right in the heart of the matter. Right? Now I'll give some not examples, but explain how one actually constructs such forms on fractal. This construction was done by already some time ago by a group of people, including Martin Barlow, with collaborators Kusuoka, Kigami, and many other Goldstein, many other people who actually actively worked in this direction, and they were able to construct local regular Dirichlet forms on many families of fractals. Right? So how one can do this? Just very briefly, idea of construction. Most of fractals can be, or maybe all of them, can be considered as limits of sequence of approximating graphs. For example, Sierpinski gasket one can consider as limit of such sequence of graph approximations. Right? This is basically the same picture of Sierpinski gasket, but with removed all interiors, just considering only the boundaries of the triangles. So that we made out of them graphs. On each graph, it's easy to construct a Dirichlet form, discrete Dirichlet form, just by a very simple formula. Gamma n denotes the nth approximation here, and En of Ff, where f is the function of gamma n, is very simple, simplest Dirichlet form, just the sum of fx minus fy squared over all neighboring vertices, right? For example, these two vertices are neighboring, they are used in this sum. And then one needs to consider a renormalized limit of such forms when n goes to infinity, and one needs to introduce some renormalization sequence, Rn, denoted here by Rn. And the whole point is whether such sequence exists and whether limit exists for large enough family of functions. This set of functions must be dense in L2. Right, and also the limit should not be zero, but identical zero, right? It should be finite and positive for enough family of functions. That's the whole point right here. And turns out that on so-called PCF fractals, post-critically finite fractals, I won't go into details. For example, Sierpinski gasket and Vicek trees are in this class. One actually can show that construct this sequence as geometric series. Rho to some power, where rho is some number specific to this fractal. For example, rho is 5 over 3 on Sierpinski gasket, and rho equals to 3 on Vicek set. Right? And then one actually can show there is certain monotonicity in this sequence, which implies existence of limit. Right? For Sierpinski carpet, this construction was much more complicated. Turns out this doesn't work immediately, at least nobody knows whether it works. But after a series of works, one showed that one can construct such a sequence that is of the order of some rho to power n. Right? This was a very difficult work of Martin Barlow and Rick Bass that actually who first constructed diffusion process on Sierpinski carpet without using Dirichlet form. But then later it was modified to construct also Dirichlet forms. Right?
Because in this case it's quite complicated, so it's not rational.
No, it's not so simple. But actually, this value of rho is not even known, right? There is this existence theorem. Right. Some numerical simulations will give this value, but we don't know. Nobody knows, right, what it is. But nevertheless, existence of this Dirichlet form was proved. Right. There are other methods of constructing strongly local on Sierpinski carpet, but also based on some of the results of Barlow and Bass. It was later by Kusoko and Zhou, and also by myself and Meng Yang later. But I will mention a little bit about that below. So now we come to the notion of walk dimension. What is there? It actually appeared naturally in these constructions, right? In all the above fractals and in many other fractals, turns out that this constructed strongly local Dirichlet form, by the way, returning to the previous question, all these forms respect the symmetries of the fractal. Symmetry and self-similarity, they all respect that. Of course, otherwise it's not so interesting, right? So this Dirichlet form possesses the heat kernel, right? And moreover, the heat kernel, what is most surprising, at least for me, satisfies on all these fractals the following estimate, which is called sub-Gaussian estimate. Estimate look like this. D denotes here distance. Actually, on these fractals, all these fractals, distance is extrinsic Euclidean distance. Alpha is Hausdorff dimension. Right? There are two parameters, alpha and beta, involved in this estimate. Right? Alpha is Hausdorff dimension, and beta is this new parameter. That's exactly the walk dimension, right? Again, the walk dimension can have the same characterization through the mean exit time. Having this estimate of the heat kernel, one actually get that mean exit time from any ball of radius r is of order r to power beta. So, and what is this beta here, right? Now a relation of this beta to differential calculus is, of course, not direct, but it's through this old construction. Dirichlet form determines, on one hand, the local operator, generator, that is determined, that determines differential calculus. On the other hand, the heat semigroup has generator, which is the heat kernel, and heat kernel is determined, at least in terms of estimate, by using the parameter beta, walk dimension. So there is some indirect link between beta and generator. In fact, that's why I'm saying that the walk dimension can be regarded as numerical characteristic of differential calculus on such spaces. Right. So what is known about this value? First of all, it's always at least 2, I will say below y. And moreover, what is interesting also, for any pair of alpha and beta, where alpha is at least 1 and beta is between 2 and alpha plus 1, one can construct metric measure space, moreover, which is also geodesic metric measure space when distance has some nice properties, with heat kernel satisfying exactly this estimate, right? So in fact, alpha and beta here can take quite a big range of values, right? And this range of values is shown on this diagram. This is alpha beta plane. beta is at least 2, right? This the lower border, and this is beta equals to alpha plus 1, the upper border of this domain. And all this shaded area, do you see these shades here? Maybe not, it's invisible on the screen. Yeah, all this shaded area, right, is a possible range of these parameters. Euclidean spaces take here very little. These are beta equals to 2 and alpha is integer. These dots, black dots, corresponds to Euclidean spaces. As you see in the family of all such spaces where nice integral and differential calculus exists, Euclidean spaces take very little in terms of, I don't know, just a few dots compared to the whole two-dimensional area, right?
I think in this fractal like thing, we have a fractal space. I think there is actually.
Well, I don't know. Of course, if one can define in some way measure on the whole space, I don't know. That might be interesting to see if there is certain density here, so one can investigate. Yeah.
On this point,
I don't know, right? Well, anyway, at this moment it's just this area, and here are dots corresponding Vichek set, Sierpinski gasket, Sierpinski couplet, right? I just mentioned it. But every other point is also corresponding to some fractal space. So this construction was done by Martin Barlow. It's a very nice construction, right? Okay. So, this is the same thing that I already shown on the picture in words. Given here values of alpha and beta for these three fractals, examples of fractals. Now I come to the main point here, to what is this value beta, right? It came from probabilistic construction, right, and from estimate of the heat kernel, right? But now I'll give it in different way, which is more suitable for analysis on spaces. Right? We start with Ahlfors-regular metric measure space, right? This is the main assumption that we make, basic assumption that we make, that this Ahlfors-regular metric measure space, and then define on this space a family of Besov function spaces. This family is 3 parameter, B, sigma, PQ. Sigma denotes degree of differentiability, how many derivatives, roughly speaking, it has, and P and Q, integrability parameters. Right? This space is LP, LQ. Well, we don't really need the full range of these spaces, so I'll need only B2 to sigma and B2 infinity sigma, so I'll give separately these 2 definitions, which are much more transparent than general definition of Besov space. So B2 to sigma consists of functions from L2, such that the following seminorm, this is B2 to sigma seminorm, is finite. And this is exactly the integral that we already have seen. Fx minus fy squared divided by distance between xy to power alpha plus 2 sigma, right? D mu x, d mu y. And B2 infinity is some modification of that when one of the integrals, okay, which involves also infinity, means there is some supremum, and this supremum is appearing here, right? Some little modification of this situation, right? So this space B2 to sigma, one can actually easily see that it shrinks when sigma increases, right? It becomes smaller and smaller, and define sigma star as critical value of sigma is supremum of all sigma when this space is still dense in L2. Right? Space shrinks, and at some point it actually collapses. For example, in Euclidean space, When sigma becomes 1, it collapses. It's no longer dense, right? So, but when sigma is smaller than 1, then it's always dense in L2 because, in fact, it contains all Lipschitz functions with compact support. And Lipschitz functions are dense in L2. Right? So the sigma star is always at least 1, therefore. Right? This critical value of this exponent. Right? In Euclidean space, as I said, this critical value is equal to 1, while on fractal spaces, it's actually strictly larger than 1. So we use this family to determine this sigma star. In fact, the most interesting value for us is critical value. Right? Yeah, yeah.
In space,
It's trivial.
usually
Yeah.
use second difference.
True, true. Yeah, but here we don't. Right. That's very good remark. In Euclidean space, when one defines Besov spaces, when one goes through threshold 1, one adds more term there, right? But here we don't do, because we don't want to have full scale of Besov spaces. We want exactly to detect the place critical value when it's degenerate, right? Yeah, that's a bit different from definition of Besov spaces. Here, Besov spaces is defined in the same way for arbitrary sigma, but when sigma is big enough, it becomes trivial. That's all. We don't go further. It's not quite Euclidean Besov space. It's just, one could say, pre-Besov space. Okay, anyway. And moreover, here we don't have possibility to add second derivative. Right? Okay, here is what is interesting. This theorem was proved by myself, Jashinho, and Kasing Lau. Suppose that EF is strongly local Dirichlet form on some metric measure space. At this moment, the metric measure space is arbitrary, and we assume that the this Dirichlet form, its semigroup, has a hit kernel that satisfies the sub-Gaussian estimate of the same type as I mentioned above on all fractals, right? For some positive alpha and beta. Then the following is true. First of all, this space has to be alpha-regular, right? Here, alpha-regularity comes from assumption about hit kernel estimate. Secondly, this value of beta, which appears in hit kernel bounds, must be twice sigma star, where sigma star was defined by using family of Besov spaces, right? As soon as we know that this space is alpha-regular, we come back and define this family of Besov spaces. Alpha is needed to definition, right? And then we can say what a sigma star is, and turns out beta must be twice sigma star. And domain of this Dirichlet form must be exactly this Besov space with second parameter infinity. Right. And moreover, the Dirichlet form itself, quadratic part, should be comparable to the Besov seminorm. Right. So what is interesting here? Coming back to one of this previous question, this the fact that beta is 2 sigma star means that the value of walk dimension is determined uniquely, right? There is no other way. If it's actually determined by sigma star is invariant of the space itself, and therefore beta is also, right? And another consequence of that, this alpha and beta themselves are invariant of the metric space MD alone. Right. We started with metric measure space, but as a matter of fact, they are independent of the choice of measure here. And the reason for that is very simple, because as soon as alpha is determined and measure mu is alpha regular, we know that in this case measure mu is comparable to Hausdorff measure. If we come to the definition of Besov spaces and replace measure mu everywhere by Hausdorff measure with comparable measure, the spaces do not change, right? Therefore, critical parameter will not change. Therefore, critical parameter doesn't depend on the specific mu. It actually will depend only on metric in this case, right? So therefore, All right. And using this result, we can actually change completely the point of view, right? Now, originally, log dimension was defined by using diffusion, Dirichlet form, and so on and so on. But now we can forget about all this and say that let us redefine the log dimension simply as twice times sigma star, where sigma star is defined, of course, in this way by using the family of Besov spaces. Right? We start with alpha-regular metric space, right? Then say mu we can take as Hausdorff measure. Then using that we define the family of Besov spaces, define the critical value of exponent when Besov spaces degenerate. And then let us say the log dimension of this space is exactly twice sigma star, right? Therefore, in this way, we obtain that log dimension is defined on every alpha-regular metric space. And therefore, this is what is main message of this talk. We have a second invariant of metric spaces. The first one is Hausdorff dimension, of course, but there is another one which is hidden, which we don't see, because Hausdorff dimension we see its measure of the balls and so on and so on. It's all geometric one, right? But there is another invariant of regular metric spaces, which is the log dimension, which is not obvious because it's hidden in the definition of Besov seminorms. We don't see them visually, right? But if we compute those spaces, we see when they degenerate, and we obtain the second invariant of metric spaces. Right? I think this is most interesting outcome of all this discussion. Right? And for that, we don't need heat kernel or anything else, don't need Dirichlet form, just start with measure, Hausdorff measure, define the families of Besov spaces, right? Which are, for that one only needs distance function and measure, as on this one can see it, and then just trace the critical value of the exponent sigma, right? So in this way, of course, one sees once again that log dimension is really invariant. It doesn't depend on anything else, just on metric. So here is some kind of characteristic of classification of metric spaces, regular metric spaces, according to the log dimension. It's similar to two-dimensional diagram alpha beta that I showed before, but here just I show only beta direction, assuming alpha is fixed, right? So this red half line is all possible values of beta. It starts from 2 and becomes it takes arbitrary values. Right? Euclidean spaces all sit here, and also many manifolds sit here when beta equals to 2. Right? These are yellow. They see yellow, right? Yellow dots. These are fractals that I mentioned above: carpet, gasket, Wittek snowflake, and there are many more of them. Every point here can be realized on some fractal, right? But there is here one more place one more point that appears here, infinity, exact infinity, not just going to infinity, right? Of course, original log dimension couldn't be infinity; it should be real number. But if we come back to this new definition, twice sigma star, and look at what is sigma star is here. Sigma star is supremum of something. Supremum can be infinity, right? By definition. Right, so in fact, it actually can occur, but with this new definition, right? And then infinity occurs in particular on so-called ultrametric spaces, which include spaces of p-adic numbers, which is very interesting, because spaces of real numbers sit on this end of this diagram, spaces of p-adic numbers sit on this other end of diagram, and between them all fractals. This is the whole picture of all these nice alpha-regular metric spaces. Right. So I say a few words about alphametric spaces. So what are these, first of all? And what are spaces of p-adic numbers? A metric space is called ultrametric if it satisfies a stronger triangle inequality. Instead of sum in the right-hand side, we get maximum of two distances. This innocently looking improvement of triangle inequality, in fact, has drastic consequences. I'll say a few words about that. But major example of such ultrametric spaces, why it's worth considering, is the field of p-adic numbers. Right? P-adic distance is defined as the mode of x minus y, well, p-adic mode of x minus y. And p-adic mode, p-adic norm is, maybe I recall definition here, if z is rational number, then its p-adic norm is defined as p is prime number, of course, p2 minus k, when provided z can be represented in the form p to power k, k is some integer, times rational a over b, where a and b are not divisible by p. Right? So the larger is k here, the smaller is the norm, p-adic norm. And one can actually easily prove from this definition that the norm satisfies this following ultrametric norm, the ultrametric triangle inequality for the norm, which implies ultrametric triangle inequality for the distance function. Right? And then the space QP of p-adic function is completion of Q with respect to p-adic norm or p-adic distance, and of course it inherits also ultrametric. Right? And then one can also go further and define QP to the power n, like Rn, but this is n-dimensional space of p-adic numbers, and then introduce the max distance. The distance between 2 points in this space, x, y, is maximum of all p-adic norms of the components. Right? And one can, this obviously also is ultrametric. And then one needs measure, and measure in this space one can use the actual Haar measure, which is n-regular. It's a measure of ball of radius r is of order r to n, and this also comparable to the Hausdorff measure. Right. So then a few words now about general ultrametric spaces. Suppose MD is alpha-regular ultrametric space. Right? Then ultrametric property implies very interesting thing. Actually quite elementary geometry, right? Suppose B is some ball of radius r in ultrametric space. Then it turns out that every point inside this ball is a center. Usually Euclidean ball has only one center, but in ultrametric space you can move this point inside the ball and every one will be its center, right? So this ball doesn't depend on the choice of the center. Right. In particular, if one has one point, arbitrary point x inside the ball and arbitrary point y outside the ball, then distance between them must be at least r, because x is the center. Right? It means that you cannot actually approach to inside the ball from exterior. Right? If we move this point y and point x, arbitrarily you never come close. They never come close. And actually, it has drastic consequences for analysis. For analysis, when you integrate fx minus fy divided by distance of xy, when distance xy becomes small, you get some singularity. Here, distance will not be small if x is inside the ball, y is outside the ball, which implies that indicator function of the ball is continuous function. It's a little bit difficult to imagine. Indicator function, which is shown by blue here, right, is actually continuous. This, although visually it has discontinuity, but it's not, because distance between points inside and outside always big. They cannot approach each other, right? And moreover, this indicator function actually belongs to Besov space for arbitrary sigma, because there is no singularity in denominator when you divide by dxy, right? which implies that sigma star is infinity, because if indicator functions in the Besov space, then of course Besov space is dense in L2, right? For every sigma, and supremum of those sigmas is infinity. So critical value in this case is infinity, and therefore beta is infinity. This is why the ultrametric spaces appear at the other end of this scale when working dimension is infinity. Right. And one more maybe interesting remark about ultrametric spaces, that also it follows from all these considerations that every ultrametric space is totally disconnected. It doesn't have connected sets except for single points. In particular, such spaces cannot carry non-trivial diffusion process. Diffusion process with continuous trajectories, of course, they don't exist, except for trivial one, right? So therefore, of course, one cannot then try to construct local Dirichlet form or local operator, differential operator, in the sense that I wanted to do this. Such spaces do not carry such operators, which also corresponds to the fact that beta is infinity, right? But they carry a lot of jump processes. For example, Besov semi-norm determines a regular Dirichlet form with the domain which is second Besov space, and the hit kernel then exists and satisfies the jump type estimate for every sigma here, or S is 2 sigma, right? But maybe it's not very essential at this moment. Yeah, now maybe I'm approaching to the end. Maybe I say some words about open questions about construction of local Dirichlet forms. As I mentioned, on fractal spaces, there has been big activities about construction which uses specific structure of the spaces, approximation by graphs and so on, symmetries and so on, right? But now let us ask a more general question. Suppose that M is alpha-regular metric measure space, could be self-similar as fractal. Actually, not on all fractals this construction has been done. And now we assume that this critical value of sigma is finite. If it's infinity, one cannot hope to construct anything, right? So does there exist a strongly local regular Dirichlet form on M? If it exists, then, or maybe one can add one more question, to construct such a form such that the hit kernel satisfies the sub-Gaussian estimate, right? To mimic the same as happens on fractals. I think that's perhaps it's too much to ask. Perhaps one needs some additional conditions. Then, of course, the question is, what are those conditions, right? When one, first of all, when it's possible to construct strongly local Dirichlet form, and secondly, whether hit kernel should satisfy very nice sub-Gaussian estimate. Second, of course, is much stronger. So here is some proposal how one can actually try to do this, right? First of all, one needs to fix this value sigma star, right? And for any sigma smaller than sigma star, we just consider the Besov semi-norm, right? But then suppose we actually can construct some quadratic form, not necessarily equal to this, but maybe comparable to this, just to have some flexibility, right? And then one needs to be able to pass to the limit, this limit, when sigma goes to sigma star. But then one should renormalize this E sigma by multiplying by sigma star minus sigma. And if this limit exists and in good enough sense and determines a strongly local Dirichlet form, this is the question, right? Whether one can do this in general. This construction works, certainly in Euclidean space, it's well known, right? In this case, one can get exactly equality here, right? For Sierpinski gasket and Sierpinski carpet, we realized this method with Meng Yang, my former PhD student. And actually it turns out to be on carpet is not easy, right? The construction is certainly not easier than it was done before by different methods. But why I advertise this approach? Because it could give universal approach without using specific structure of the space construction of local Dirichlet forms. And construction of local Dirichlet form is, of course, from my point of view, is equivalent to construction of differential calculus on such spaces. So we start with Besov seminorm and try to use this to approximate to come in the end to local Dirichlet form. Right. So in this construction, if it works, has also advantage because one can have some formula for the Dirichlet form as limit, at least as limit of something computable, right? Not just some abstract Dirichlet form which exists by some existence theorem, but maybe something more computable. Right? And of course, I'm finishing one more open question related to that. Of course, the precondition for this construction is this sigma star. One needs, well, I wouldn't say to know this, but at least to have some knowledge about this critical Besov exponent, right? So, and the next question is how to be able to determine the critical value of sigma, even for fractals in general. Of course, this question contains very difficult particular case when this fractal is Sierpinski copied. Already 30 years, it's not known what is the exact value, so therefore I don't expect this question to be solvable easily. But what is tempting to do is, if any fractal is determined by the first step in its construction. Sierpinski gasket is completely determined by this picture, right? This triangle with the removed middle triangle. Sierpinski copied determined by this picture, Wiczek set determined by this picture. Therefore, the work dimension or critical sigma should be invariant of such graphs. These are graphs, right, basically. Well, what could it be? These are rather small graphs, right? I cannot imagine that this should be a very difficult thing, but it turns out it is. But what is this? How one can describe critical value of Besov spaces in terms of one of these graphs, right? As invariant of this graph. First step in the construction of fractal space. All right, by that I finish, and thank you for attention.
Any questions?
Thanks for Professor for this like interesting talk. And I see that this talk is about like generalizing the ordinary fractal analysis on the n-dimensional Euclidean space, I think. And I wonder if we can do some more generality. And for example, so I think can we consider even the topological space with some more properties because like in general topology things are defined more like the general topology is studied by many years and there are lots of conditions. But normally we don't care about these conditions. But I think there may be some conditions useful to discover like more generality. And I think perhaps we can do another generality in the algebraic, like in algebra, like we can consider more like algebraic space, like more than just a periodic version. I also don't know a lot about it, but I just think it may be like a thought or something. Like, can you comment on this?
Well, I don't know about other structures. This is what I was telling about. All is linked to notion of distance function, right? Metric, right? Nothing else. Basically, one needs metric, right? Therefore, in topological and these invariants, both Hausdorff dimension and work dimension are determined by metric. If you change metric, you change them. Of course, therefore, from that point of view, I don't see what one can do on topological spaces. This is completely.
I believe that there may be Euclidean notion.
Like to lessen the motion of metric because the metric has the axiom and the prediction axiom.
Well, I don't know, quasi-metric or something. I don't know. This is at least one to try. But at this moment, even working with metric spaces brings up a lot of interesting problems, right? At this moment, I wouldn't. Of course, presence of various algebraic structures might be interesting, in addition maybe to metric or something. Well, I don't know. Again, as a matter of fact, many locally compact groups actually have this ultrametric structure. So in fact, they are included in this ultrametric consideration, right? I don't know other examples. Maybe there are some other classes, algebraic classes, which can have specific properties of the metric. I don't know, but it might be interesting. But again, it's all about the metric, right? If you want to try go away, it will be different theory. Right. Yeah.
Thank you for your talk. I have two questions. The first one is, can we define some work dimension for the non-negative curvature manifold for the work dimension?
Sorry, for which? For work dimension?
For the negative curvature manifold.
But negative
use the
curvature.
log of volume.
Well, I don't know. Of course, for say, if you take hyperbolic space, right?
Yes.
Then expected value of the mean exit time from ball of radius r for large r will be of order r, for large r, right? Because on hyperbolic spaces, Brownian motion goes away almost linearly. Yeah, the work dimension will be in this case 1, so it's smaller than 2, because its volume is not polynomial, volume is exponential. So in principle, one could define the work dimension, right? But it doesn't fit this theory. For that one needs a different one. For this theory, one actually uses heavily the fact that volume of balls is polynomial one, volume doubling. This can be generalized to volume doubling. On spaces of negative curvature, typically will not be satisfied. Typically will have exponential volume growth. It's a very interesting question as well, what one can do in such situation, right? Of course, if you have already manifold, you don't bother with existence of local Dirichlet form. It always exists, right? This on any manifold, this always exists, right? But you can ask about how quickly Brownian motion goes away, which basically amounts also to heat kernel bounds, right? It's related to the fact that heat kernel in time decays exponentially, and how exponentially it actually amounts to the bottom of the spectrum of Laplace operator. Basically, one could reformulate this. Maybe there is some constant. Maybe one can ask something about this constant or whatever. Right. Right. Question makes sense certainly, but in different way. In probabilistic way, it makes sense, of course. Yeah. One can ask whether one could have different values. For spaces. Yeah, I think it's doable, but it goes a little bit different direction. Yeah.
I have another question. For special type of Ahlfors-regular site is the limit site of some Klein group of hyperbolic space. So are there some results for such fractal site?
Well, I don't know. I don't know.
Also, do we have any other similar notion of work dimension for graphs, simply for complexes, or lattices of general manifolds in the discrete sense?
Yeah, in discrete situation on graphs, of course, one can have the same, right? Basically, first of all, for random walk, one can ask the same question, right? If on any graph one has simple random walk, one can ask the same question. This is probabilistic way, but for, yeah, I think this question makes perfect sense, and also related to fit kernel bounds on such situation, right? On discrete situation, there is no problem with defining anything. Dirichlet forms or random walk, everything exists. Then the question becomes quantitative, how to estimate it.
I have another quick question. Are there any like a study on the? I have heard about random graph. Are there any study on the fractals on random graph?
Yeah, there is big theory of percolation. These are instead of fractals, right? This constructing of random graphs by randomly removing some edges, right? And then one obtains percolation. These are big connected sets after that. And then actually one can investigate all these properties on such percolations. And they also have very many properties of fractals.
Yeah,
right.
Yeah. The random walk on random graph.
Yeah, right. Yeah, random walk in random environment. Yeah, that's actually it's quite big area. In fact, originally it was before fractals. This percolation theory was before fractals. Fractals appeared later, and in fact, as first they thought about fractals a kind of deterministic approximation to this random graphs. But then these two theories kind of deviate. They become independent of each other. But in fact, yes, you are right. Many things exist there. In particular, hit kernel bounds and so on also exist on percolations.
Okay, let's send the speaker.